Welcome to this final video lesson on radioactivity. The lesson objectives for this video lesson are as follows. State that nuclear decay is spontaneous and random. Define and use the terms activity and decay constant. Infer and sketch the exponential nature of radioactive decay. Solve problems using x equals x0 e to the minus lambda t, where x could represent activity, number of nuclei, or count rate. Define the term half-life. Derive the relationship between half-life and decay constant. And then finally solve problems using lambda equals ln2 over t a half. So the focus of this particular video lesson, which is at the back of the theory of radioactivity, is to model radioactivity mathematically. So when an unstable nucleus undergoes radioactive decay, it transforms. Now, what does this mean? Well, it means that the number of atoms in the original sample decrease over time, and that the number of emissions per second drop over time. So let's start off with the definition of activity. So activity, represented by capital A, of a radioactive sample is the rate at which nuclei decay or disintegrate. So as soon as we refer to rate, we are referring to a ratio with respect to time. So in the denominator, there will be a time value. So A is measured in decays per second, and it's named after becquerel. So 1 becquerel, or 1 BQ, is equal to 1 decay per second. It's critically important to note that nuclear decay is spontaneous, and it's spontaneous because the decay of an individual nucleus is not affected by the presence of other nuclei. So the decay of a specific nucleus is independent of the nuclei around it. And the decay of nuclei cannot be influenced by chemical or physical changes, example, temperature or pressure. So spontaneous means that it just happens. So one cannot predict it with absolute certainty, and it's not influenced by that which is around it. So this leads into the fact that nuclear decay is random because it is impossible to predict when an individual nucleus in a sample is going to decay. So this is critically important. There is no way of predicting when a particular nucleus in a sample of radioactive material will actually decay. Each nucleus in a radioactive sample has the identical chance of decaying per unit time. So this leads us now to quantifying the decay. So the decay constant, lambda, is defined as follows. The probability that an individual nucleus will decay per unit time interval is called the decay constant. And as I've mentioned, we use the Greek letter lambda. Let's look at an example. A sample of a radioactive isotope has 1 million nuclei. So the fact that it's radioactive means that each of those atoms in that sample has nuclei which have the capability to decay into a daughter nucleus, into something else. So after 1 hour, it is found that 200,000 nuclei have decayed. So remember, if they've decayed, let's say for instance they were originally element X, now that they've decayed, they would be a different element. Let's say for instance element Y. Let's say for instance it was alpha decay. So the nucleus would change, the number of protons would change, and so therefore it would be a different material, a different element. So find that after 1 hour, 200,000 nuclei are no longer of element X, but now are element Y. So this would mean that lambda, the decay constant, which remember now is the probability that of an individual nucleus decaying per unit time, we find that there's 200,000 nuclei that decayed out of 1 million. So that's the probability. So we're going to find that that's 0.2, but this is the probability per unit time. Notice it was the probability per unit time interval. So this is important. It's not just, lambda is not just the probability, it's the probability per unit time. So this is going to be 0.2 per hour. So the unit for lambda, the decay constant, is either seconds to the -1, minutes to the -1, hours to the -1, days to the -1, or years to the -1, depending upon the radioactive isotope and how quickly it decays. So the activity is proportional to the decay constant. So the higher the decay constant, in other words, the higher the probability of that type of nuclei decaying per unit time, obviously the higher the activity is going to be. And it's also important to note that A is proportional to the number of undecayed nuclei. So the more undecayed nuclei there are, the greater the activity. But as the number of undecayed nuclei falls off, as you will later on, you will see in this lesson, then the activity decreases. So this implies taking the dependency of the activity on these two parameters, the decay constant and the number of undecayed nuclei, we get that the activity is equal to lambda multiplied by n. Note, lambda is the decay constant, that's the probability of a nucleus decaying per unit time interval, multiplied by the number of undecayed nuclei. We can also express activity in the following way, as A is equal to the rate of decay. So this would be the change in the number of nuclei per unit time. So the change in the number of nuclei would be that amount of nuclei which have undergone the decay. So we see here delta N is the number of emissions or decays, and delta T is a small time interval. Now, looking at units for A, 1 becquerel is 1 decay per 1 second, and that's a small unit. But generally speaking, especially with very radioactive samples, you have a much higher activity. So 1 CI or 1 curie is the activity of 1 gram of radium-226. So that works out to be 3,7 times 10 to the 10 becquerel. In other words, that is 3.7 times 10 to the 10 decays per second, which is 37 billion decays per second. So let's now look at something called count rate. So it is practically very difficult to determine the true activity of a sample directly because we cannot easily detect all the radiation emitted. So the radiation generally gets emitted into space, three-dimensional space. So we are definitely going to have some radiation that will escape past our detectors, and some radiation may even be absorbed by the sample itself as the radiation is on its way out. So we can use several different radiation detection systems. The most famous one is the Geiger counter in order to detect and measure radiation. So if we place the counter in front of a radioactive sample source, it will only detect a fraction of the activity A of that source. So if we know how efficient our Geiger counter is, we can deduce A from R. So the count rate measured by our Geiger counter would be R. Okay? So R is what we actually measure. That's the count rate. But the count rate is not the true activity of the radioactive sample. So a typical setting in which a Geiger counter could be used would be, for instance, in a gold mine. On the Witwatersrand Gold Basin. So that's up in Gauteng, where there is this huge reef that runs across Gauteng, and we see there in the ores radon and its daughter isotopes are prevalent due to the presence of uranium and thorium in the host rocks for the gold-bearing ore. So yeah, in this context, these materials could be tested for by means of using a Geiger counter in the close proximity to the ore. So let's look at some examples of how to use the quantitative models of activity, radioactivity, to solve certain problems. So the first one is, a sample consists of 1,000 undecayed nuclei of a nuclide for which the decay constant is 0.2 per second. So that would be 0.2 becquerel. Determine the initial activity of the sample. Estimate the activity of the sample after 1 second. So there's two parts to this question. The first is to estimate the initial activity. Now remember that the activity is proportional to the number of undecayed nuclei. So it's going to fall off, it's going to decrease as time goes on, because as decay takes place, the number of undecayed nuclei is going to decrease, so therefore the activity is going to decrease. So let's start off with the initial activity. I'm going to symbolize that with capital A 0 for t equals 0, or for the original activity, and this is going to equal lambda multiplied by n, the decay constant multiplied by the number of undecayed nuclei. Now substituting for lambda 0.20 seconds to the minus 1, and substituting for the number of undecayed nuclei initially, 1,000, and now multiplying them together, we get that the original or the initial activity is 200 decays per second, or 200 becquerel. So as I've just mentioned, this implies that 200 nuclei decay per second initially in this particular sample. Now let's look at the second part of this question. We now want to determine the activity at 1 second. So now the number of undecayed nuclei is the original amount of 1,000 minus the 200 that initially decayed, and that is now 800 undecayed nuclei, keeping in mind that the decay constant is dependent on the type of the nuclide, the type of radioactive material. So it stays 0.2 seconds to the minus 1. So the activity at 1 second is going to be the decay constant, which is just that, it's constant for that material, multiplied by the number of undecayed nuclei at 1 second. And that's going to give us 0.2 seconds to the minus 1 multiplied by now 800. And therefore the activity after 1 second is equal to 160 becquerel, which implies 160 decays per second. So we can already see that the decay rate has fallen off. Let's look at a second example. A radioactive source emits beta particles. It has an activity of 2,8 times 10 to the 7 becquerel. Estimate the number of beta particles emitted in a time interval of 2 minutes. State one assumption made. This comes from Sang, Jones and Woodside. So the activity is 2,8 times 10 to the 7 becquerel. Now that's the initial activity, because remember we said that the activity falls off. Using the fact that the activity is equal to the rate of change of the number of nuclei per unit time, and so n would be the number of undecayed nuclei, but the change in the number of undecayed nuclei would actually be the number of nuclei that have decayed in the time interval delta t. Changing the subject of the formula to delta n by multiplying by delta t on both sides, we get that delta n is equal to the activity multiplied by delta t. But this is assuming A is constant, and that is the assumption, which, depending upon the time interval, if this is a significant time interval, this becomes more and more inaccurate. The smaller the time interval, the more accurate it becomes. So in actual fact, we should actually be working with the derivative of n with respect to t. In other words, A equals dn by dt, where dt would be the infinitesimal time interval. But we are not working with calculus at this stage. So this is an assumption, and we can see here 2 minutes is quite a significant time. So delta n equals A delta t, with delta t being 2 minutes, is probably inaccurate. So substituting n for the activity, 2,8 times 10 to the 7 decays per second, because it's becquerel, multiplied by the time, which must be in seconds, because becquerel is per second. So in 2 minutes you have 2 times 60 seconds. This is going to equal the number of emissions, and that's going to give us the total number of emissions to be 3,36 times 10 to the 9, and we have noted that this is obviously going to include a fairly high uncertainty or error. So now, looking at the fundamental mathematical law that governs nuclear probability, the activity of a radioisotope decreases gradually as a function of time. And that should make sense. Radioactive decay follows a very specific pattern, that of exponential decay, which we will explicitly use in a mathematical form soon enough. And no matter the type of radioactive isotope, it will undergo the same pattern of decay, namely exponential decay, as shown below. So if we look at this graph below, this is a typical radioactive decay graph. So what we see here, and this is really important, that if we look over a time interval where the original sample of radioactive material has decreased by a half, and if we say, we call that time interval t, then what that means is that in that time interval t, the number of undecayed nuclei has halved. So as you can see here, we have a representation of all the undecayed nuclei. But at t, only half of the nuclei are left over, that when we say that, undecayed, in an undecayed state. Now, this time interval we call the half-life. And the half-life is dependent on the type of material and the radioactive decay constant. The higher the decay constant, the smaller the half-life is going to be, because if it has a higher decay constant, it's going to decay quicker, which means it's the time interval for it to decay to half of its original amount of undecayed nuclei is going to be much less. So now if we look at the next interval t, so this is the same amount of time as from there to there, what we find is that once again it halves. So we see here, if this is the amount of nuclei left over after t, then over the next t interval, half of this is now what's left over. So in other words, half of these nuclei have decayed, going from n over 2 to n over 4. So let's say, for instance, this was 1,000 nuclei initially, undecayed. This would be 500. This would be 250. This would be 125. So this time interval is the time that it takes this amount of nuclei of this nuclide to decay to half of the nuclei. And if we go again, we'll see that this time interval, same amount of time, is once again from n over 4 to n over 4 divided by 2, which is n over 8. And so we can see here that the gradient or the slope of this curve continually gets less. And theoretically, this is asymptotic. This should never get to 0. It should only get to 0. It should only touch the t-axis at infinity. So this is a typical exponential graph, but it's a decay graph. So we're going to see that in the exponent of the exponential graph, it's going to have a negative exponent, and we'll see that soon enough. So the equation to represent this exponential decay is shown below. So, and here it is. So the number of nuclei at a specific point in time, n, and that would be the number of nuclei that remain undecayed after time t, is given by the formula n equals n0, where n0 were the amount of undecayed nuclei originally, and then this is where the decay comes in. So that shape of graph, the base, is what they call the natural logarithmic base, and we use the symbol e in mathematics, and that base is equal to 2,71828. Now that may seem to be an arbitrary number, but this is in actual fact the base that we find in nature for natural growth and decay processes. So as I mentioned before, the exponent is going to be negative because it is a decay process instead of a growth process. The decay constant lambda is there, and then obviously this is a function of t. So t being the amount of time that is lapsed between when the number of undecayed nuclei was n0 and at the specific point in time. So we could explicitly write it as follows, as n is a function of t, so that's the number of undecayed nuclei in the system of radioactive nuclei at a particular point t, equals the number of undecayed nuclei initially multiplied by the natural base or natural logarithmic base e minus lambda, which is the decay constant, multiplied by t. So this explicitly shows that this n value is a function of time. Now, since the activity A of a sample is proportional to the number of undecayed nuclei in the sample, then the activity also decreases in the same way. So we can get that the activity A, as we've already discussed, is also a function of time, and it is equal to A0, and once again E minus lambda t. And just to reiterate, this is because of the fact that the activity is proportional to the number of undecayed nuclei in the sample. So if we look at this representation here, we see it talks about a parallel decrease in the number of nuclei and the activity. I would like to mention, however, that this should be more, this shouldn't be linear, but should be more curved, as it is in actual fact an exponential graph. So if we now look at the following, it says, usually for the reasons explained under the description of count rate, we measure the corrected count rate R in a laboratory rather than the activity or the number of undecayed nuclei. So we use a Geiger-Miller counter, for instance, and the Geiger-Miller counter gives us the R, the count rate measurement, and not the activity. And since the count rate is a fraction of the activity of a sample, it too decreases exponentially with time, as we can see here, because it is dependent on the activity. And so it too follows this same mathematical form. So here now what we've done is we've actually summarized the mathematical models for the number of nuclei, undecayed nuclei in a radioactive sample for as a function of time, the activity of decay at that particular point in time, as well as the counter reading, that the counter rate at that particular point in time. So and they all have the same form, and so that is quite beautiful. It also is very nice because it makes things simpler. So now we come to a very important question. What is the relationship between the half-life, T1/2, and lambda? Now, we have already discussed this qualitatively. As the lambda increases, as the decay constant increases, that means that the probability of a nucleus decaying per unit time increases, which means that if you're looking at the amount of time it is going to take a radioactive sample to have its undecayed nuclei halved, that is also going to decrease. So therefore, as the lambda increases, T1/2 decreases. So this would be a negative relationship. So as the one increases, the other one decreases. So let's just state that again. That's a qualitative relationship. We are going to look at a quantitative relationship. Keep in mind that when we look at it qualitatively, as the lambda increases, the probability of decay for a particular nucleus increases per unit time, which means that the time required for the sample's undecayed nuclei to halve will decrease. Now, starting off with the relationship, then n equals n0 e minus lambda t, which we've already discussed, n being the number of undecayed nuclei, n0 being the initial amount of undecayed nuclei in the sample, and then e being the natural base or the natural logarithmic base, minus lambda, the decay constant, multiplied by t, the time. So this is a function of time. So if we substitute t equals 0 into this, then we substitute 0 for t here. Then lambda times 0 is going to give 0. And any base to the power 0 is going to give us 1. So e to the 0 will be 1. 1 times n0 is n0. So at t equals 0, that's the boundary where the system starts. We get that n is going to equal n0, which we knew. Now, if we look at t equaling T1/2, or what we call the half-life, then over this time interval, the number of undecayed nuclei is going to halve. So it's going to go from n0 to n0 over 2, or half n0. So now we can state, well, that n equals half of n0, which is n0 over 2, when the time is equal to the half-life. But using this equation, n equals n0 e minus lambda t, at T1/2, then n is going to equal half n0. So we land up with this equation. A half n0 equals n0 e minus lambda T1/2. Now, mathematically speaking, n0 cancels in this equation. because we can divide by n0 on both sides. So a half equals e minus lambda t a half. Now this is pretty significant, because what this is saying is that the nature of the graph does not depend on the initial starting condition of this particular system. Now a half is the same as 2 to the minus 1. If we take 2 to the 1 across the division line, we make the exponent negative. So t to the negative 1 equals e to the minus lambda t a half. And now, using basic algebraic skills, in order to get rid of the negative in the exponents, we are going to raise both sides to negative 1, which we're allowed to do. And using laws of exponents, if you've got x to the m raised to the power n, then it's x to the m times n. So 2 to the negative 1 to the negative 1 is the same as 2 to the negative 1 times negative 1, which is positive 1. And negative times a negative is positive, so negative 1 times negative 1 is positive 1. So we're going to now say, well, this is the same as 2 to the 1, which is just 2. On this side, e to the negative lambda t a half to the negative 1 is the same as e to the negative lambda t a half times negative 1. A negative times a negative gives us a positive. Lambda t a half times 1 is lambda t a half. So there now we have this equation. Now we're going to make use of something that you might not have dealt with in mathematics yet in grade 11. To my knowledge, this is done in grade 12 in the standard mathematics syllabus, but if you do AP mathematics, then you might very well have already done this. So this is the definition of a logarithm. It goes as follows. If a number n equals b to the x, now this n is not necessarily the number of nuclei, this is a general number n. So if n equals b to the x, this implies the logarithm of n to the base b equals x. So let me give you an example here. So let's say, for instance, we have that 100 equals 10 to the 2. Then this is what we call exponential form. This will be exponential form. Right, and you've been working with this since early high school. This is a different way of writing this. So this means that the logarithm of the number 100, when viewing it with respect to base 10, then the logarithm is that number which you have to raise the base to in order to get the number. So in order to get 100, you have to raise the base 10 to a power of 2. So therefore your logarithm will be 2. Let's try another example. So let's use a different base. So let's say, for instance, I've got that 64 equals 2 to the power. Now, I'm not going to give you the answer. All right, we're going to get it just now. Then this implies that the logarithm of the number 64 with respect to base 2 is going to equal that number, which when you raise 2 as the base, then if you raise that base then to whatever number, and that number is actually the logarithm, then you get 64. So in this case, what is that number? Well, 64 is 8 squared, and 8 is 2 cubed. So we have 8 squared is 64, and we know that 8 is 2 cubed squared. So 2 to the 3 times 2 is 6. So this number here should be 6. 2 to the 6 should give us 64. 2 times 2 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. And 32 times 2 is 64. So therefore the logarithm of 64 to the base 2, let me say that again, the logarithm of 64 to the base 2 should be 6. So in actual fact, the logarithm is the index or the exponent that you have to raise the base to in order to get 64. Now, you might be thinking, wow, we are really complicating matters here. Why would we do this in the first place? Well, the reason why logarithms are so beneficial is because of the laws of logarithms. So when you do logarithms in AP, Math, or in grade 12, you will come across some of the laws. So instead of multiplying powers of the same base, you will add their logarithms. Instead of dividing powers of the same base, you will subtract their logarithms. So this results in a linearization of numbers. And it's interesting that when you do pH, for instance, in chemistry, that the pH, and I will write it down here. I know this is a physics course, but I think most of us know pH. The pH of a solution is the negative logarithm of the hydronium ion concentration to the base 10, which means that the concentration of hydronium ions in a solution is 10 to the negative of the pH. All right, now I don't necessarily expect you to know how to do that yet. Basically, you divide by or multiply by negative on both sides. So this becomes negative pH equals the logarithm of the hydronium ion to the base 10. So the hydronium ion is going to be 10 to the negative pH. Right, so that's obviously in chemistry. The Richter scale is the Richter scale used to measure the intensity of an earthquake, is also logarithmic. So we do find the logarithm as being a very useful way of modeling certain phenomena. Now, why am I talking about this? Well, we have a situation that fits into this model here. So we've got n equals b to the x, but now our n is 2, our base is the natural base, base e, and our x is lambda t a half. So switching now from exponential form to logarithmic form, our n is 2. So we're going to have the logarithm of 2. Our base is e, so we have the logarithm of 2 to the base e is going to equal lambda times t to the half, which is our x. So we have converted this equation from an exponential form to a logarithmic form. Now in mathematics, we represent log base e by ln2, which we call ln2. Now, I know ln is L-I-N phonetically, but we're going to just say ln. Log base e is ln2, which you're soon enough going to see is actually found on your calculator. And so now we make lambda the subject of the equation, that's the decay constant, by dividing both sides by the half-life, t a half. So that's going to give us lambda equals ln 2 divided by t half, which is the half-life. Now, if we take a look at a standard calculator, non-programmable calculator that we use at school, so this is my Casio, and we go and search for ln, we find it right here. So we're going to find it right here. And remember, this is log base e. This is known as the natural logarithm. And if you look carefully, you'll see In the second function, you have e to whatever exponent you want to raise it to. To the left is what we call the common logarithm. This is log base 10, which is known as the common logarithm. This is the common logarithm, and in a slangish colloquial way, we, instead of calling it a logarithm, sorry, and up here I should have put logarithm. Instead of calling it a common logarithm, we can call it the common log. Right, and you will see above it, there we have 10 to whatever exponent you want to raise it to. Then if you want to use different bases, like for instance log base 3 or log base 2 or log base 4, then you would use this button here. So for instance, if you wanted log 7 base 4, then you would use that button. So now if you press lin 2, then you are going to get that lin 2 is equal to 0.693 rounded off to 3 decimal places. So we can then use this form of the equation, that lambda equals 0.693 over the half-life. Now, I would prefer you to remember it as that lambda is equal to the logarithm of 2 to the base e, or ln 2. So I would prefer you to remember this form when working with the relationship that links lambda to t a half. Now, recall before we proved this that we referred to the qualitative relationship. And so if you look here, remember I said to you it was a negative relationship. Well, if the half-life increases, because it's in the denominator, if you increase the denominator, then you're decreasing the overall number. And so therefore, the decay constant will decrease. So working the other way around, so if your decay constant decreases, which means the probability of decaying per unit time is decreasing, well then your half-life is going to increase. In other words, it's going to take longer for that radioactive sample's number of undecayed nuclei to decay to half of that amount. And so if we decrease t a half, then this is going to increase the decay constant. Looking at it the other way, so if your decay constant increases, then the probability of a nucleus in that sample decaying per unit time will go up, which means that in a particular time more nuclei will decay, which means that the half-life, the time that it takes for that radioactive sample's amount of undecayed nuclei to decay to a half, will decrease. And so here we can see that the quantitative model of the relationship between the decay constant and the half-life fits in beautifully with the qualitative model that we discussed before we proved this. So let's now look at a practical application, that of cobalt-60, which is used in radiation treatment for cancer. Now, if we look at the decay graph for cobalt-60, on the vertical axis, we have got the amount of cobalt-60 remaining percentage-wise. So you can see the maximum value is 100%. So the 100% would correspond to the initial amount of cobalt-60 in a particular sample. So yeah, it would be 75%, which would mean that 25% of the original sample's cobalt-60 would have decayed and would no longer be in cobalt-60 form. So if we look along here, this is the number of half-lives. So this is the time, but in multiples of half-life. So I mean, we could put T here if we wanted to, and it would be measured though not in seconds but in half-lives. So if we look at this, we can see that after one half-life, only 50% of the original sample of cobalt-60 remains. So if the original sample was 10 grams, then after one half-life, only 5 grams remains. Now, if we look over the next half-life, then which takes us to 2 half-lives, then we have that half of the 5 grams remains after this next half-life. So that means only 25% remains. If we look over the next half-life, then half of that decays, which takes us to 1,25 grams left over. Why? Because 1,25 grams of this sample decayed. And so we go on. And so, strictly speaking, we should never really get to a point where there's 0 grams of cobalt-60 remaining. But in practical terms, it comes to a point where it will no longer be a useful sample of cobalt-60 in order to carry out its treatment, the treatment required. So the half-life of cobalt-60 is 5,27 years. So when it comes to half-lives, this is sort of sitting in sort of an average half-life. You get half-lives that are a few seconds, a few minutes, and then you get half-lives of certain materials that are thousands and millions of years long. So the important thing here that I would like to bring out is that the half-life cannot be manipulated. This is a quantity or a property of a radioactive nuclide that cannot be manipulated by humans by changing temperature, changing pressure. This is statistical. It's based on probability of a nucleus in that nuclide that has yet to be undergo decay of decaying per unit time. So this is a fundamental characteristic or property of that substance. So it's dependent on that particular type of isotope. So cobalt-60 has a half-life of 5,27 years because it has a very specific decay constant. And I challenge you to work out what that decay constant is using the formula that we have just derived. Now, for any radioisotope, the intensity of radiation is directly proportional to the rate of decay and the amount of substance. Therefore, a cobalt-60 source for radiation treatment must be replaced regularly to remain effective. So you wouldn't want to use a depleted cobalt-60 source, which would require a person undergoing treatment to sit for days on end in order to be treated effectively, in order to get enough intensity of radiation treatment from the sample, because it has so little undecayed cobalt-60 nuclei left over. So in practice with radiation treatment, the source of the radiation, the cobalt-60, has to be monitored so that it is feasible to treat the person in a short time frame and to do so effectively. So let's consider another example. We've got cobalt-60, which decays with a half-life of 5,27 years to produce nickel-60. Now note, cobalt has got 27 protons and nickel has got 28. So there is an increase in the number of protons by 1, but the total number of nucleons doesn't change. So what type of decay is this? Well, it shouldn't, and certainly wouldn't be alpha decay, because remember, with alpha decay, the helium nucleus takes with it 2 protons and 2 neutrons. So the proton number would decrease by 2 from 27 to 25, and the nucleon number would go from 60 to 56. So this is definitely not that. But we're getting an increase in the proton, so this must be beta minus decay, because a neutron is being converted into a proton. That's why we're getting an increase in the number of protons by 1. But the total number of nucleons doesn't change, because the neutron changes into a proton, which is still a nucleon, and we get a high energy electron, which is the beta minus particle. And we remember we get a anti-electron neutrino that comes out as well. So it's beta minus decay. So what is the decay constant for the radioactive disintegration of cobalt-60? Well, that was the challenge I set for you just now. And then the B part, calculate the fraction of a sample of the cobalt-60 isotope that will remain after 15 years. So this is the type of problem you would get in tests and exams. We don't aim to test you on extremely difficult problems. We just want you to have a basic idea of the mathematical model of radioactive decay and being able to solve simple problems on this. So we have that the half-life is 5.27 years. We were given that. Using the mathematical formula, lambda equals ln 2 over t half. And substituting for t half, 5.27 years, we get that the lambda, or the decay constant, is 0.132, and because the unit for the half-life was years, the unit for the decay constant is years to the -1. So what does this actually mean? Well, it's telling us that in a period of a year, the probability of one nucleus of cobalt-60 decaying is 13.2% probability. Right, so 0.132 is the same as 13.2 over 100. So there's a 13.2% chance that a cobalt-60 nucleus in a radioactive sample of cobalt-60 would decay in a 1-year period. So in physics, it's always very important to look at the answer to a mathematical problem and then to try and physically interpret its meaning to the physics and not just getting a mathematical answer. Now looking at the second part of the problem, calculate the fraction of a sample of the cobalt-60 isotope that will remain after 15 years. So using the formula, the number of undecayed nuclei at a specific point in time equals the original number of undecayed nuclei, the radioactive nuclei, multiplied by E minus lambda t. Rearranging this equation to n over n0 by dividing by n0 on both sides, we get that n over n0 equals E minus lambda t. Now can you see this is the fraction of a sample of cobalt-60 that is left over. So it's that which is still left over at time t over the original amount of undecayed cobalt-60 nuclei at the beginning, at the start of when this sample was used. Now substituting for lambda and t, we worked out that lambda, the decay constant for cobalt-60, is 0.132 per year, so we substitute in there. Don't forget the minus sign, because remember this is radioactive decay. It has to be a decay. This needs to continually be decreasing, and that does that when the exponent is negative. So it's negative 0.132 years to the minus 1 multiplied by the time in that unit, 15 years. And this gives us an answer of the fraction of n over n0 being 0.138. So converting that to a percentage, that means that 13.8% of the original sample of cobalt-60 is still undecayed. In other words, still radioactive. That percentage of the original sample is still able to and is going to decay. Let's now look at a third question. So how long does it take for a sample of cobalt-60 to disintegrate to the extent that only 2% of the original amount remains? So starting off with n over n0 equals E minus lambda t. We now substitute for the fraction 2 over 100 because 2% is the actual fraction left over, 2 over 100. And then we substitute for the decay constant for cobalt-60, which is 0.132. And remember that was per year. And now, because of the fact that our unknown is t and it sits in the exponent of this power, we are now going to use the definition of the logarithm, which says that if n equals b to the x, that implies that the logarithm of n to the base b equals x. So we're now going to use this. And that gives us that the logarithm to the base e of the number 2 over 100 is equal to the exponent negative 0.132t. So let's just go through this again. So if n equals b to the x, then the logarithm of n to the base b equals x. So we've got ln, which is the logarithm to the base e. So the logarithm to the base e of the original number, so we're trying to describe this number as a power with a base e. Then in order to do that, the exponent is the logarithm, is negative 0.132t. So what we've done now by using this, we have brought the t, which was in the exponent of this power, downstairs, so that now t is downstairs, and so we can now easily solve for t. We now work out what ln 2 over 100 is. So on your calculator you type in, you punch in ln 0.02, and that will give you negative 3.912. And now we have a nice linear equation free of logs. And when we divide both sides by negative 0.132, we get that t equals 29.637. And remember that the decay constant's unit was per year, or year to the minus 1, which means that the time it will take for the sample of cobalt-60 to decay to the point where only 2% of that original sample is now radioactive, in other words, still has undecayed cobalt-60 nuclei that have yet to decay to nickel-60. That is the time it would take, 29.637 years. So we can see 2% is very little. They would probably not be using a 2% radioactive sample to treat a patient who has cancer. But we can see that it's only 30 years, approximately 30 years, before it becomes virtually depleted. So even though mathematically it would take infinite amount of years for the sample to disappear completely, and so that there's no nuclei in it that are radioactive, in practice it's not the case. So we have now reached the end of this module on radioactivity, and we are going to move into the next topic, which is cosmology, astrophysics and cosmology, which is going to be fascinating and we are going to make use of our knowledge of nuclear physics and radioactive decay in this next module. But before we do that, I will assign as homework a few problems on radioactive decay that you will need to work on before we move on to the next module.